So Darryl sent me a bio, but I took the liberty to rewrite it. Darryl is a human earthling. As an Eagle Scout back on Earth, he loves all outdoor oxygen activities. From backpacking to scuba diving, and most certainly sports. In high school, in the Philadelphia area, he wrestled, played football, and rugby. At the University of Pennsylvania, he double majored in physics and math. And now he has a first-year PhD in the astronomy department. His research interests include, and here it goes, solar astrophysics, cosmology, specifically magnetohydrodynamics, helioseismology, gravitational lensing, and dark energy. You should try making that into a rap, Darryl. And he will tell us what all these mean in his stellar astrophysics talk. Please help me welcome Darryl.
So it goes from very passive to very active, back to passive. And so in 11 years, it's from passive to active. And that's another thing, we really don't understand that at all. So I want to talk to you guys today about stellar astrophysics, or just more commonly known as the study of the stars. First though, I just want to say how inspiring it is to me that so many of you guys are here today, and you took your free time on a Sunday to come and learn about science from grad students, because it really reinforces this idea that I have, and this idea I've had has actually been proven to me over and over and over again throughout my life, and that's that people are fascinated by the universe, and people love science, and it actually might be a little more fundamental than that. I think that as humans, we inherently have this drive to want to figure out what's happening in the universe and our place and kind of unravel the mysteries of the cosmos. So I don't think there was ever anyone who, it was a clear night and they went out and looked at the stars and saw the Milky Way, and they didn't wonder what the stars were and how they got there and what our place in the cosmos is, okay? And I'm not talking about just today. I'm talking about throughout time. So all throughout ancient civilizations, one constant is that all civilizations looked at the stars and made constellations. So they were looking at patterns in the stars and projecting what they saw in the natural world into the heavens. So one constellation that everyone knows is the Big Dipper. And this is a Greek constellation. The Greeks thought that the Big Dipper, or Ursa Major, was a bear. But the Egyptians actually thought that the Big Dipper looked like a hippopotamus. And so, okay, what was going on here? So they didn't have bears in Egypt, but they actually did have hippopotamus. So they were taking what they saw in the natural world and projecting that onto the stars. And what's so cool is that the other way around was also going on. So there's this theory that the 3 pyramids of Giza were actually built aligned with the 3 stars in Orion's belt. So the sun was actually central to the Egyptians' religious belief. So their main god was Ra, and Ra was the god of the sun, and he was the most powerful god in the Egyptian mythology. And depicted here is Ra on his boat. And every day, as the sun goes across the sky, Ra is supposed to be carrying the sun in his boat across the sky. And then at sunset, Ra goes into the underworld. And that's shown here. Ra is actually fighting the serpent Apep, who was, according to the Egyptians, the lord of chaos. And what's cool to me is that the reason that the sun is so central to their religion is central to their lives, right? Like their whole livelihood was based on the sun because their crops grew because of the sun. And so there have been a lot of theories about stars throughout human history. I just want to show this clip real quick.
Moon. Yeah. Ever wonder what those sparkling dots are up there?
I don't wonder. I know.
Oh, what are they?
They're fireflies. Fireflies. They got stuck up in that big bluish black thing.
Oh, gee. I always thought they were balls of gas burning billions of miles away.
With you, everything's gas.
But what's funny to me, actually, is that as little as Timon knows about the stars, we really aren't in that much of a better place right now. So we know very little about the stars. And it's kind of crazy to think, because if you think of the universe, in astronomical terms, the sun is one of the closest astronomical objects to us. But we really don't know that much about it. We know more than Timon, but... So yeah, so Pumbaa's right, okay? These stars are these big balls of gas. But they're not passive. They're actually extremely active and volatile. And there are big solar eruptions that happen all the time. So it's like on Earth, there are volcanoes going off every couple of weeks. And they can be big solar flares or coronal mass ejections, which are basically a big explosion, and then the mass from the sun is ejected into space. And this is a video that was taken in April 2015 from the Solar Dynamics Observatory. And it's a mass ejection they labeled the Phoenix Prominence. So the video kind of speaks for itself. It's really awesome. But watch here. There's going to be a big explosion. Here. Yeah. So it's pretty amazing that we have the technology now to actually see it like this. But one thing I want to point out is that this was actually taken in extreme ultraviolet light. So this is really high energy light that you're watching, and you would not be able to see this with the naked eye. So actually, you see all these bright spots on the star? Those actually appear dark if you're looking in the visible light. And so the question is, what are these dark spots on the sun? So first in the 1600s, Galileo discovered that there were sunspots, and he observed things like this. And scientists later discovered that these sunspots, or we now call them active regions, they have a lot of magnetic activity. And the magnetic activity makes the temperature go down. And so it shines less bright. So it's not that they don't shine, they just shine a lot less bright than the rest of the star. And now if you zoom into the sunspot, they actually come in these pairs. So this is actually a north-south magnetic pair. And just like if you've ever had a bar magnet, or a couple of bar magnets, and the north and the south ends attract to each other, that's the same thing that's going on here. And scientists realize that it's these active regions that actually are associated with the big explosions. So the coronal mass ejections and the solar flares happen in these active regions. So they figured that the magnetic activity must be what was behind the solar flares. And there's this idea that they came up, that this process that they observed, right, it's called magnetic reconnection. And here's a paper from 2015 of, this was before, during, and after the flare. And actually, these loops, the particles are frozen into the magnetic field. So you're actually seeing the magnetic field at the surface of the star. And the idea of magnetic reconnection is you have a big loop, and then it's in a really high energy state, and then these field lines break, and they reconfigure themselves in a lower energy configuration. But this energy has to go somewhere, so that's the energy that goes into the coronal mass ejection or the flare. So here, look, you've got a high energy state of the twist of the magnetic fields, then it breaks here, and then it's a lower energy state. And it's when it breaks there, that's when the flare happens. And another thing I want to stress is, even though I'm telling you about this, we really do not understand this process. So we see it happening, but we don't have a good grasp of the physics behind it. So it's a very active part of research right now. And it's a really exciting time because the National Solar Observatory is building a huge solar telescope in Hawaii. And we're going to be able to observe magnetic reconnection with much better resolution. And that's coming online in the next 5 years, so it's a really exciting time for solar physics. Okay, so now with this in mind, I want to show you another coronal mass ejection. This happened in June of 2015, but I want you guys to watch for the magnetic reconnection during the flare. So first we just got a full disk view of it. Here's the flare, or the mass ejection. And now it's going to zoom in, and I want you guys to look at the field lines and look at the high energy before the flare, then during, here's the high energy, right? So we've got high energy configuration, it breaks, and now, well, wait for it, now we've got the big explosion, and we've got a lower energy configuration. So yeah, to me it's so cool that we have technology that we can watch this going on right now. So, besides from the fact that it's really cool, why do we care about this? Like, why is the government funding people like me to do research on this? Well, the sun is actually one of the only astronomical objects that directly impacts our life on Earth. So every time there's a flare or a mass ejection, all of that mass and energy and magnetic flux, that's coming straight to Earth. And when that hits Earth, it messes with our GPSs, it messes with satellites, it messes with airplanes and power stations. Actually, it causes billions of dollars in damages every year. So the government really wants to find out the mechanisms behind the solar flares so that they can prevent these damages. Another reason that we want to study the sun is that we want to understand the properties of all of the stars in the universe. And there are tons of stars in the universe, and stars are just like people. They're born, then they grow up, then they get old and they die. And the sun, our sun is a grown-up star. But we want to, by figuring out what's happening with the grown-up star, we want to extrapolate and figure out what's happening with all ages of stars. This is an exciting point, actually. Another reason we want to study it is a lot of astronomers now are looking for planets that are in other solar systems. So these are planets that orbit other stars. They call them exoplanets. And one of the ways in which you find an exoplanet is, so if you're observing the star, you look for the change in the light when the exoplanet passes in front of the star. And so, okay, say this projector is the star, and then my hand is the exoplanet. So you're watching, you see how much light is coming to the screen, and then this exoplanet goes by, and when it's in between us and the projector, there's less total light. Now, the issue is that, say you're looking at another star and it gets a sunspot, or it gets a solar flare. If the light is changing due to the star's activity, how do you distinguish that from the exoplanet? So this is one of the most active fields of research in astronomy today. A fourth reason is another application of how the sun affects life on Earth is every time there's a solar storm, it produces these beautiful auroras. And actually, there was a solar storm last week, and you could see auroras not that far north from here. And so, yeah, that's the end of my talk. Thanks for listening to me.